Honorable experts, distinguished guests, ladies and gentlemen, good afternoon. We are from the School of Mechanical Engineering in Tianjin University. It's my honor to present our work with you. More than 70% of the Earth is ocean, and the ocean contains a large amount of natural resources, which provides a solution for mankind. However, there are many dangers in the oceans, as well as the fact that humans cannot work in the ocean for a long time, so we have to use some tools to explore the resources of the ocean. Currently, underwater robots have a wide range of applications in ocean exploration and underwater operations. They are an important technical means for mankind to understand and explore the oceans. Traditional underwater robots use propellers for propulsion. The propellers rotate to push the current, thus generating a reaction force to propel them to navigate. But these robots have the disadvantages of bulky size, poor mobility, low propulsion efficiency, and large environmental disturbance, which to a certain extent limit the development and application of underwater robots. To meet the needs of underwater robots in terms of propulsion systems, people focus on underwater organisms, among which fish have attracted many researchers for their high flexibility, mobility, propulsion efficiency, and biocompatibility. The propulsion modes of fish could be divided into two categories, which are body and cattle fin and median and paired fin, and the manta ray studied in this work belongs to the latter. In 2003, Osaka University researched a pectoral fin-propelled robot and then built a manta ray-inspired robot, laid the foundation for the development of pectoral fin-propelled mode of robotics. By studying manta rays, we are committed to creating a low-noise, highly biophilic manta ray-inspired robot that is expected to have some practical applications. We realized high speed and stable multi-attitude motion of the robot by studying the motion system, designing the drive system, researching attitude regulation, and analyzing the hydrodynamic properties. There are three innovations in this work. Firstly, a bionic fin structure based on tensegrity was designed, which has good fatigue resistance and expansion compensation. Second, the shape of the robot was optimized by computational fluid dynamics simulation to achieve highly bionic characteristics. Third, remote control of the robot was realized. Tensegrity is considered to be a structure that can reproduce the motion of manta rays. In this work, we completed the assembly and testing of the tensegrity by studying tensegrity and rope deformation. Based on the mathematical model, the motion parameters of the manta ray-inspired robot was established and the force analysis was carried out, and a control method based on the pivot mode generator was designed, which can effectively improve the motion adaptation ability of the robot. We also established a simplified physical model of the manta ray fins, based on which we carried out a force analysis of the tensegrity, established a dynamics model of the system through the Euler-Lagrange equations, and carried out simulation analysis through MATLAB, obtaining the variation of the torque and power of the motor over time, as well as the influence of the parameters of the size, mass, and stiffness on the dynamics of the system, and analyzing and deriving the optimum parameter. Thereafter, we derived the optimal propulsive efficiency and the lift-to-drag ratio curves of the robot through computational fluid dynamics simulation analysis. The lift-to-drag ratio curves of the robot are highly similar to those of the real manta ray, which achieves a relatively excellent bionic effect. After assembling the model, flap tests and underwater tests were conducted. The robot is capable of multiple forms of motion, such as straight swimming, turning swimming, yaw and pitching, with a speed of 0.9 body lengths per flap. Finally, there are the parts of the design of this work and a comparison between the model and the prototype. The above is the whole content of the manta ray-inspired robot. Thank you for your attention.